So, welcome everybody to this afternoon session. I am Helmut Seidel from TU München, and I will chair this session. Our first presentation is about misconceptions about loops in C. So, please go ahead.
Hi. Hi, everybody. Is this working? Classic start to a talk. Is this working? Hi, I'm Martin. I don't really know what loops are. This is Mahdi. He does. I'll talk to him afterwards. all entry edges go to the same location. So this is on entering. All entry edges go to the same location. Seems fairly reasonable. Oh, what the hell is this? This, of course, is Duff's device. If you haven't come across this, this is a technique that was proposed by Tom Duff for realizing that switch just have to go to labels. There's nothing to stop you hiding a loop inside your switch, at which point where you jump to in the loop depends on your variable. And it's really handy if what you want is your compiler to optimize those 4 and do them as a block, but also not have to do a separate loop where you do 1 to 3 of them. So it's really compact, produces really nice code if you're a 1980s compiler, and it's very much still out there in the world. What's not as widely known, though, is there are worse versions. Duff's device is not as bad as this gets, right? There's an amazing paper, we cite it and I've forgotten the author. Somebody says, hey, you realize you can build reentrant state machines like this in C. It's fine, just use these macros. And they're using this trick. It's horrendous. It's in putty. So if you've SSH'd in from Windows, you've used this. Another one. Do we want another myth? I don't know. How much time have we got? 10 minutes. Okay, we definitely want another myth then. Somebody else had their hand up further back. Which, at the end of a loop, so this will be under exiting. Oh, inside. The end of a loop is an unconditional jump, right? This is very much the kind of thing that we said we're teaching people. Okay, well, let's see if it's true. The end of a loop is an unconditional jump. No. No, it's not, because do while loops, you might wind up with a conditional jump at the end. Okay, now is this the one that I'm like, you can fix this with one unrolling? I can't remember. No, it's not. So yeah, this one, you might wind up with your last instruction being conditional jump. So, what else? What other myths do you think your students might fall for? Not that I'm giving you exam questions or anything.
Back edges are the same as backwards jumps.
Oh, I love this one. We actually had a genuine bug report on this. God knows what they were doing to make it happen. Second to last. Definitions. Oh, definitions, my bad. Oops. So, if your code is compiled up, if you're using the list of instructions representation, and you're like, oh, it's fine, we can find loops because they've got back jumps, then, and some idiot writes this. So, go to A, go to B, go to C, then you're clearly going to have a backwards jump. But of course, when you feed it into a control flow graph, whoom, like that, like the magician, it all just straightens straight out. Simple, right? Oh, and we've lost our back, so I have to go back. Okay, any more? Should we do some more? What other myths are there? I'm going to pick him because he hasn't asked. Yeah. Oh, I love this one. Again, almost all of these, like at some point, me or somebody I'm working with has screwed up. And this one, we took so long realizing what the hell was going on. Inlining is harmless, right? You might inline for performance. You might inline just so you don't have to do context-dependent analysis. You might inline something like this. So we've got a function, nested loops, we return out of the nested loops and at the end. Reasonable, well-behaved code-ish. Doesn't involve any go-tos. Now, when you inline that, if you're not careful, you may wind up with something you can only express with a goto. Because if you align this code into another loop, what you will wind up with are exits from inside, not just out of one, but out of several loops, and into an outer loop. We found this one by scanning this, looking at the source examples. They're all well behaved. There are no go-tos here. Going back through all of the handling of the control flow graph. Where the hell are the go-tos coming from? Turns out the answer's in lining. I'm going to be cheeky and pick the next one because I like continuing this theme. Gets me, I can tell a joke. So it gets more fun though if you implement jump threading. I tried to look this up whether it has an official name, but this is the optimization where if you're a go-to or any kind of conditional control flow and your target is an unconditional go-to, then you might as well just shortcut, right? Harmless operation, right? Couldn't possibly screw things up. So if you take the previous one and you inline it and then do jump threading, then what you've got is a jump from anywhere in the body of this function to here, or likewise to here. Now, this is not quite an uncontrolled go-to, but it's almost there in terms of the level of chaos that you can generate. So this led to me saying that I feel like both breaks and returns are like domesticated go-tos, but breaks are domesticated in the same way dogs are domesticated, and returns are domesticated in the same way that cats are domesticated. So, anyway, Chair, how much time have we got? I should stop this now. 5 minutes. Okay, should we do one more then? One more. If you want any of the others, then you're going to have to read the paper, I'm afraid. Or you can ask Mahdi, because he knows them all. One more? Loop. Oh, okay, well, this is quick. Not all loops have contents. So if you want to busy wait, you can often wind up with a loop that just doesn't have anything in it, and this is a perfectly legitimate thing to find in your code. But of course, if you've got a API function which says return me the body of the loop, then if one made a mistake like that, then you'd ship code out and you'd find it crashing at some point with a null pointer exception and no obvious answer as to why, because clearly there's got to be something in the loop, right? I'm going to pick one more just because I like the amount of chaos that it can bring. So you start out by a simplification. Oh, but it's fine. It only removes edges. Doesn't change the number of loops you have. How about this? So we've got a macro that just tests whether a pointer is read-write. And we've got a pair of nested loops. So we've got 3 loops. Right? Or do we? Because maybe actually you're doing this slightly later on and you've already got rid of this. So maybe we've only got 2 loops. But maybe actually you already know something about P. Maybe it's a pointer to a local variable. So you know that this will always be side effect free. So it's fine, you can optimize it away. It doesn't do anything. Now at this point, if you remember back to your definition of natural loops, you'll find that you've got 2 natural loops, but they share the same head. So the only sane solution is to treat them as one loop. So, depending on how much you know about P and where in your optimization process you do this, this is either 1, 2, or possibly 3 loops. Right, I really should stop this. So conclusions. We came up with 4 recommendations, which is that if you're designing APIs for working with loops, design for the general case. Design so that your API function is not give me the loop entry point. It's give me the entry points. And then maybe you have a separate flag, separate function for, is this a single entry loop? But always design for the more general case, because it's really hard to go back and undo that. Secondly, put preconditions in. It is totally morally acceptable and fine to go, we are not going to handle some of the horrible, horrible cases, but you should check that. You should put a precondition in, and you should give a meaningful error message, because trust me, later on when your tool becomes popular, people start submitting insane bug reports. Yeah. Also, if you have multiple uses of loops, if there are several points in your code where you touch loops, like, you know, early on you look at instrumentation and then later on you're doing, I know, loop acceleration, expect that you'll have to track between them. Because as we show, loops can vanish, merge, appear from nothing. Yeah, just the, oh, it's fine, we did loop analysis back there, that'll still hold here. Not true. Last one, systematic test cases. So definitely talk to Mahdi about this. We have a collection of the horrors that are in the paper as useful standalone test cases, which hopefully have assertion failures when you miss a path. We are actively trying to distribute them. If you have any other horrors that we've missed, please do let us know. Anyway, thank you very much for your time and attention. You've been incredibly patient. And I think that's all.
Thank you. Thank you very much. Other questions?
Thank you very much. I was wondering about the distribution, if you plan to submit it to like something like the software verification competition or NIST tests or something.
I've thought about submitting it to SV Comp, but I don't know whether they'll let me into the building again afterwards. Like just trying to run these through CBMC, which doesn't necessarily do any particularly fancy loop analysis. We've found not only some like really exciting weirdnesses, we've also found horrible things like, well, this is clearly showing exponential behavior, but we have no idea why. So yes, I think we should. I'd quite like to, but I don't know whether anyone will ever speak to me again if I do, because some of these are horrible.
I think some other people submitted some horrible stuff, and that's part of the competition.
I had a small hand in some of the floating point stuff, so yeah, okay, and people still talk to me. Fair, fair.
So one more question.
Great talk. I think the obvious question is, how many loops do you have in your slides?
Oh, Jesus. Before we started, afterwards?
Internally and externally.
Oh, Jesus. I mean, do you count the hyperlinks? You know, do these count as loops? In which case, I think it's about 17 or something.
I guess it's one strongly connected component, maximal strongly connected component.
I hope so, but like, I mean, there are some hidden slides at the end that you have to ask me about if you want to see them. So I don't know if they're connected. I'm sorry, I don't know the answer.
Okay, thank you very much.